In crystal binding, today we are going to discuss the problem of calculation of binding energy of crystals of inert gases. Actually, the crystals of inert gases are molecular crystals, and the atoms in this molecular crystal is bonded together by a weak force which is called actually van der Waals force. And our basic problem of today's lecture is how to calculate the binding energy or the lattice energy of this molecular crystal. Okay. So, first of all, we will see just as a revision the important properties of this molecular crystal, which are actually inert gases crystals, and after that we will see what type of interactions take place between the atoms of a molecular crystal, and taking those interactions under account, we will be able to find the binding energy of this molecular crystal. Okay. Actually, as I have told you that the crystals of inert gases are molecular crystals. Okay. And these molecular crystals are composed of atoms which are actually whose valence shell, or you can say the outermost shell, are completely filled with electrons. As you know, the outermost shell of inert gases is completely filled with electrons, and so you can say in this case too, the outermost shell or the valence shells of this of the atom of this molecular crystal are completely filled. And if the outermost shell will be completely filled, then such an atom will not lose electron. Those atoms will not gain electron or even share electron to form the chemical bond. So in this case, neither the ionic bond nor the covalent bond is formed, because ionic bond is formed by the complete transference of electron, and covalent bond is formed by the sharing of electron. But since in this case the outermost shell of the atom are completely filled with electrons, so this atom has neither a tendency of losing electron, nor a tendency of gaining electron, nor the tendency of sharing electron. So there will be no covalent bond, no ionic bond between the atoms of a molecular crystal. Okay. And that's why in this case actually atoms are not bonded together by such a chemical bond, ionic bond or covalent bond. Okay. In fact, if the cells are completely filled with electrons, then actually the electronic charge distribution is spherically symmetric. So in this case of molecular crystal, as the cells are completely filled with electrons, such cells are also called closed cells. So these atoms have a spherically symmetric electronic charge distribution. Okay? The electronic charge is distributed inside the atom in maintaining the spherical symmetry. Okay? Now, actually, these molecular crystals have the crystal structure of cubic closed packed FCC structure. But He3 and He4 are the exception. Actually, in He3 and He4 there is no FCC structure, but except He3 and He4, all the molecular crystals or the inert gas crystals have FCC structure in solid state. Okay, when crystal is formed, this gaseous system is in solid state. Okay. Now, actually, these crystals have very low melting point, and these are also transparent insulators. It means these crystals do not conduct electricity, so they are insulated, and light passes through it, so these are also called transparent. So these crystals have a very low melting point, and these are transparent insulated. I have mentioned it. So these were some of the important properties or feature of this molecular crystal. But our prime aim of this lecture is to discuss how to determine the binding energy of this very crystal. Okay? So let us see the steps following which you can calculate the binding energy of this crystal. Okay? And for this, let us consider there is a specimen of molecular crystal, and the specimen consists of several atoms. Let us say the total number of atoms in this specimen is n. Let us consider. And for the calculation of binding energy, we consider at first two atoms. Let us say this is our ith atom and this is jth atom. This is assumed for calculation. Now you know that there will be an interaction between this ith and jth atoms, and due to that very interaction between I and j, an interaction energy will be developed. So due to the interaction between I and j, we consider this phi ij is the interaction energy. Okay. Now let us consider that the interaction of this atom I with all other atoms. It means I is fixed, but j is not fixed. This j will be equal to 1, 2, 3, 4 and so on. And only restriction is I is not equal to j. So when this ith atom is interacted by all the remaining atoms, then due to that very interaction, what will be the interaction energy? That can be easily found by simply summing this phi ij for the all values of j. As you can see, the interaction energy developed due to interaction of I with j, only one j, is this phi ij. But when this j will run from 1 to n except I, then what will be the total interaction energy of interaction of I with all other j's? If that energy is denoted by the symbol phi I, which I have mentioned here, this is binding energy of interaction between the atom I and all other atoms of the crystal. That will be simply equal to summation phi ij for j, where I is not equal to j. Okay, I is not equal to j. Now we will see, once this phi a will be known, we can easily find the binding energy in the equilibrium state of our crystal. But before that, first of all, we will try to find phi ij. Once phi ij will be calculated using this equation 1, we will be able to find phi I, and when phi I will be known, then you will see later on how we can calculate the total binding energy of the crystal containing n atoms. Okay. So let us see first of all the calculation of this phi ij. As you know, this is the energy of interaction which appears due to the interaction between the ith and jth atom. So for knowing its value, first of all we have to think about what type of interactions will take place between the ith and jth atom. Okay? Actually, there are two types of interaction between the two atoms I and j in this case. And what are actually those two interactions? The first one is called van der Waals interaction, or it is also called London interaction. Okay, it is also called London interaction. And the another interaction is repulsive interaction. Okay, you have seen in the case of ionic crystal, this repulsive interaction was also present there, but there were no van der Waals interaction. But instead of van der Waals interaction, in case of ionic crystal, you have seen there was Coulombian interaction. But in this case of molecular crystal, the atoms are bonded together by two types of interactions. First one is called van der Waals interaction or London interaction, and the second one is called repulsive interaction. Okay. Now we will see the energy developed in our system due to these two interactions. Okay. So first of all, we will see what will be the interaction energy of I and J due to the van der Waals interaction between them. Actually, what is this van der Waals interaction? In fact, this is the dipole-induced dipole interaction. This is dipole-dipole interaction, but when the dipoles existed in this case are molecular dipoles which are produced due to the mutual interaction. So this, you can say that van der Waals interaction, which is not a very strong interaction, it is a weak interaction, and it is a dipole-dipole interaction, or we also call it dipolar interaction. In fact, in this case, dipole-induced dipole interaction takes place between the two neighboring atoms, and so as to produce a weak attractive force between the atoms. Okay? Due to this interaction, a weak attractive force acts between the atoms, and these interactions are also known as dispersion bonds. This is also called dispersion bond. Okay? And it is attractive in nature. But how it is actually developed, let us see it here. You can see, I have considered here that this sphere in left side, you are seeing in this figure, this represents the ith atom, and the sphere shown in right side of this figure, let us consider this is your jth atom. Okay, this is jth atom. Actually, due to the fluctuation in charge of jth atom, a dipole moment is induced in the ith atom, or you can say that the jth atom induces a dipole moment in the ith atom. And if you consider that the induced dipole moment in ith atom due to the charge fluctuation in jth atom is pi, then what will be the value, what will be actually the this pi is the dipole moment. Okay. Now, due to induction of jth atom, now this ith atom behaves as an electric dipole having dipole moment pi, as I have shown in this figure. Now, this atom I, which acts like now an electric dipole, produces an electric field at the site of this second atom J. Okay, and that electric field also induces electric dipole moment in jth atom. So for getting the value of the electric dipole moment induced in jth atom by the ith atom, first of all, you will have to calculate the electric field produced at the center of this jth atom due to the ith atom which is now just acting like an electric dipole. Let us see. This is this is an electric dipole, as you can see. This is charge delta and this is delta minus. This is the charge developed, positive and negative, and this is just like an electric dipole. And here is the point which is at a separation of Rij. Okay. Definitely in your elementary course of electrostatics you have studied when the test point is situated on the axis of an electric dipole, what is the electric field produced by the dipole there. Actually, the magnitude of electric field is given like this. This is 1 over 4 pi epsilon naught 2p over r cube. Okay, this is the expression in SI unit. But here we will make our calculation in CGS unit. So when you will adopt CGS unit, we will omit this factor 1 over 4 pi epsilon naught. And at the place of P, here there will be Pi, and at the place of R, there will be Rij. So you can say that if Pi is the instantaneous value of dipole moment, let us write it in vector form. Instantaneous value of dipole moment of ith atom due to charge fluctuation on jth atom. Okay? Then this dipole moment produces an electrostatic field E at the center of jth atom. Okay? And its magnitude in CGS unit is given like this. Okay? Have you understand? I have already explained these things in very detail just now. So E is given by 2 pi by Rij whole to the power 3. Okay? Now you can see our second atom, that is jth atom, found itself in an electrostatic field E, and that electrostatic field is produced by the ith atom. Okay? So this electric field E induces an electric dipole moment in jth atom. And what will be that induced dipole moment in jth atom due to the induction of this electric field E, which is produced by ith atom? You know from electrostatics that this if Pj is the magnitude of the induced dipole moment in jth atom due to the electric field of ith atom at the site of jth atom, then this Pj is given like this. Pj is equal to alpha E times capital E. Here actually this alpha E is called electrical polarizability or electronic polarizability. You can see alpha is what? This is electronic polarizability. You can watch my video in the playlist of physics of dielectrics, and there you will find a detailed discussion on this electronic polarizability. If you want to know more and more about this electronic polarizability and this type of interaction, you must watch the playlist Physics of Dielectrics of my channel. Okay? And in that chapter you will find that Pj is given by alpha E times E. But E has been already defined in equation 2. So let us substitute the value of E which we have defined in equation 2 here. And then you will get that Pj is equal to 2 alpha E times Pi over Rij whole cube. So this is the dipole moment induced in the jth atom. So now there are two dipoles. The first dipole is ith dipole and second is jth dipole. Okay? And dipole moment of ith dipole is Pi and that of jth atom is Pj. Okay? And the dipole moments of both are in same direction. Now these two dipoles interact one another, and there will be a force of attraction between them. When you study in electrostatics the dipolar interaction, then you can see there that such type of two dipoles attract one another, and due to that attraction an interaction energy is developed. What will be that interaction energy? What is the expression for that? That thing you will find in your course on electrostatics in the physics of dielectrics. Okay, so or the study of electric dipole. So see here, I have mentioned that these two dipoles interact with each other in such a way as to produce a net attractive force. Mark it. And the potential energy of this interaction is given by phi attraction, ATT. This stands for attraction. And this is given by, remember this formula. If you want to know how this formula has been written here, you have to go through the course on electrostatics and on the electric dipole. Okay. So remember it, phi attraction, that will be equal to minus 2 pi times pj over rij cube. Now let us substitute the value of pj which you have obtained in this equation 3 in this equation. So after putting the value of pj, our result becomes phi attraction is equal to minus 4 times alpha e pi square over rij to the power 6. Okay, this is actually the expression for the attractive potential energy due to the attractive interaction between two induced dipoles. Here ith and jth atoms just act like dipole. Okay. Now let us see here. You can see this equation number 3. If I will ask you that what will be the dimension of this alpha E, you can see the dimension of pj and dimension of pi, both will be same because both are dipole moments. Okay, so dimension of alpha E will be same as that of the dimension of rij cube, but rij is length, so dimension of alpha E will be simply equal to length cube or L cube. Okay, so I have mentioned it here. You can see alpha E has dimensions of length cube. Okay, and what is the dimension of dipole moment? You know, dipole moment is equal to charge into length. So dipole moment has dimensions of charge times length. Okay, so what will be the dimensions of alpha E times pi square? See it here. Alpha E has dimensions of length cube, this is L cube. Okay, and pi square. Pi has the dimension of charge into length, and since there is a square, so this will be charge square into length square. So this is simply length to the power 5 into charge square. So you can easily now say that the dimensions of alpha E times pi square will be equal to length to the power 5 times charge square. Okay. In our present situation or present calculation, the most relevant length is the atomic radius r0. Actually, this is the value of atomic radius, and this will be the relevant length in this case. Okay. Since alpha E times pi square has the dimension of length to the power 5 times charge square, so that as relevant length you can take the atomic radius r0, and relevant charge you can take the electronic charge. So dimensionally E square times r0 5 will be same as alpha E times pi square. So for an empirical relation, this alpha E times pi square may be replaced by E square times r0 5. So in the expression of this phi attraction, which has been defined in equation 4 in RHS, we can replace this alpha E times pi square by E square times R naught phi. Okay? So phi attraction is almost equal to minus 4 times E square R naught phi over Rij whole to the power 6. Now you know this E square is an absolute constant. R naught will be also a constant for a given atom, although for different atom it will be different, but its order will remain same. R naught is of the order of 10 to the power minus 8 cm. Atom to atom, something will be multiplied with this factor, but it is always of the order of 10 to the power minus 8 cm. Okay? And you know this E is equal to what? This is 1.6 into 10 to the power minus 19 coulomb. Okay? So when we will actually change this coulomb in the CGS unit and put the value of E square and R naught 5, then we get that this 4 times E square R naught 5 is almost equal to 10 to the power minus 58 arg cm6. And we have denoted this constant by the symbol C. So the expression for this phi attraction can be written as minus C over Rij to the power 6. Okay? But 6 is almost equal to 10 to the power, C is almost equal to 10 to the power minus 58 arg cm6. Okay? So this equation 5 defines the energy of interaction or potential energy which is developed due to the dipolar interaction or van der Waals interaction between the two atoms. Okay? Now you can see that this energy is inversely proportional to Rij to the power 6. So you can say that this phi attractive varies with Rij to the power minus 6. So when Rij will be slightly changed, there will be a large change in phi. If Rij will be slightly increased, there will be a large fall in phi. And if Rij is slightly shortened, slightly decreased, there will be a large increment in the value of phi attraction. Okay? So this van der Waals interaction is a short range interaction. Okay? So you can say that the van der Waals interaction, or you can also call it London interaction, that is a short range interaction, which increases rapidly with decrease in Rij. Okay? So in this way we have considered the first interaction, which is called van der Waals interaction, taking place between the two atoms of a molecular crystal, and we have obtained what will be the interaction energy. That interaction energy is defined in this equation 5. Okay? Now we will see the another interaction which takes place between the two atoms of a molecular crystal. As you have seen in case of ionic crystals, that the repulsive interaction comes into play for very short distance between the atoms. That is when the atoms are so close that the electron clouds of the atoms begin to overlap with one another, and the Pauli exclusion principle is violated or destroyed. Actually, then repulsive interaction takes place between the two atoms. Okay? And the energy due to this interaction may be expressed as a power law of the distance. Actually, in this case, it is found that energy due to the repulsive force is empirically expressed as phi repulsion is equal to B over Rij to the power 12. Rij to the power 12. Okay. And here Rij has a power 12, so it is a very, very short range interaction. It is even more short range interaction than the van der Waals interaction. Okay. And B here is a positive constant. Okay. Here the exponent of, you can say the repulsive exponent is 12 in this case. So remember it. Okay. So now you can see when there is an interaction between the ith and jth atom, there are two types of interaction, van der Waals interaction and repulsive interaction, and due to those two types of interaction energies are developed. The first interaction energy you have defined as phi attraction, and the second type energy you have defined as phi repulsion. Now when we will add these two interaction energy, then we will get actually the total interaction energy developed due to interaction between the ith and jth atom. So now you can say that the total interaction energy phi ij between the atoms I and j of the crystal will be given like this: phi ij equal to phi attraction plus phi repulsion. Okay, but we have seen that phi attraction is equal to minus c over rij to the power 6, and phi repulsion, what is this? This is b over rij to the power 12. Okay, so this is the expression for the interaction energy developed due to total interaction between I and J. Now actually for our further calculation, we will express this equation 7 into another convenient form. Actually these constants C and B are expressed in terms of two very important parameters, and those parameters are actually denoted by the symbol epsilon and sigma. How these two parameters will be defined in terms of B and C, you can see it here and you can remember, and then in terms of these two parameters, equation 7 is expressed for convenience. So when we will express this equation in terms of these two parameters, you can write phi ij equal to 4 epsilon times sigma over rij whole to the power 12 and minus sigma over rij whole to the power 6. Actually here at the place of C and at the place of B, what have been written? You can see here C has been replaced by 4 epsilon sigma 6, and this B has been replaced by 4 epsilon sigma 12. Okay, 4 epsilon sigma 12. You can substitute these two values of C and B in your equation number 7, then you will see our result is phi ij equal to 4 epsilon times sigma over rij whole to the power 12 minus sigma over rij whole to the power 6. Okay, actually the values of these parameters epsilon sigma are determined from the measurement in the gas phase of our crystals. Okay, or these constants are, you can also say that these constants are evaluated empirically. Okay, empirically. Actually this equation 8, in which this phi ij has been defined in terms of the parameter epsilon and sigma, actually this quantity phi ij is also known as Lennard-Jones potential. This is known as Lennard-Jones potential. Okay, so whenever let us say that an objective question is asked, what is Lennard-Jones potential, you have to say that this is the potential arised due to the attractive van der Waals interaction and the repulsive interaction between the two neighboring atoms of a molecular crystal. Okay, so this phi ij is also known as Lennard-Jones potential. Okay, so now finally we have obtained the expression for the interaction energy, which is developed due to the two types of interaction between the atom I and J of a molecular crystal. But until now we have not calculated the value of the binding energy of the crystal. And for calculation of the binding energy now, let us consider that in the specimen of our crystal there are n atoms. How many atoms? There are n atoms. We consider. Actually, I have told this fact early in the beginning of the lecture. Okay? And you have seen that phi I, this is the energy of an interaction or binding energy when there is an interaction between the ith atom and the all remaining atoms. Okay? So, what will be the total binding energy or total interaction energy? Since the number of atoms is n, so when you will multiply this phi I by n and the result is divided by 2, then you will get the total binding energy. Why we divide by this 1 by 2? Why we divide by n phi I by 2? Or no, why we have taken 1 over 2n instead of n? Because here interaction takes place between a pair. So the pair of two atoms is counted once. So if there are n number of atoms, the number of pair will be n by 2. Okay? Number of pair will be n by 2. And one pair is counted once. That's why to get the total binding energy, we do not multiply phi I by n, but we multiply phi I by 1 over 2 into n. Okay? And what is this phi I? You have seen earlier that this phi I is simply equal to summation over j phi I j, where j is not equal to I. Okay? J is not equal to I. And what is this phi ij? You can see it in equation 8. So let us put it here. So phi is equal to 1 over 2n times summation over j phi ij. And now we substitute the value of this phi ij from equation 8 here. And you can see phi will be equal to 1 over 2n and summation over j phi ij, this is equal to this much, which has been defined in equation 8. Oh, you can see. So this is the expression for phi. I have already mentioned here the reason behind multiplying by 1 over 2n instead of n here. I am just giving a reading, you can see. In this case, 1 over 2n is used instead of n because we count the contribution from each pair of ij interaction only once. Have you understand? Okay. Now, as you have seen that for calculating the binding energy of the ionic crystal, we have introduced a dimensionless parameter. Like that, in this case too, I am just introducing the same dimensionless parameter denoted by the symbol Pij. It has no dimension. This is just a number. And we define it like this. Rij is equal to Pij times R. Here R is what? This is the nearest neighbor distance in the crystal. Okay? So Rij is expressed as the multiple of R by this Pij. Okay? So if now your aim is to express this phi binding energy in terms of Pij, in the expression defined in equation 9, we must replace this Rij by Pij times R. Okay, Pij times R. So after doing this, what we will get? You can see that phi will be equal to 1 over 2n times 4 epsilon times summation over j sigma divided by Pij times R whole to the power 12 minus sigma over j sigma over Pij R whole to the power 6. Okay. Actually, it is found from the experiment that for FCC structures, the summation over j Pij to the power minus 12, which is present in the first term inside the square bracket, it is found that it is equal to 12.131. So you must remember it for writing this answer in your examination. Okay? It is found for all FCC structures, the value of summation over j Pij to the power minus 12, this is equal to 12.131. Okay? And similarly, it is also found for the same FCC structure, summation over j Pij to the power minus 6 is equal to 14.454. Okay? So now let us substitute the value of this summation over j Pij to the power minus 12 and minus 6 in this equation 11. So after substituting this value, what will be your result? You can see phi will be equal to, here this cancel this is 2. So phi will be equal to 2n epsilon times, now for summation over j 1 by Pij to the power 12, we will write 12.131. And the remaining factor is sigma over R whole to the power 12. And in the second term, summation over j 1 over Pij to the power 6, that's equal to 14.454. And the remaining factor is sigma over R whole to the power 6. Okay? Now, for getting the value of phi, we must know the value of sigma over R. And this sigma over R can be found by considering our crystal in the equilibrium condition or equilibrium state. You know, when R is equal to R naught, then equilibrium state is achieved. And in equilibrium state, this binding energy, this energy phi is minimum. And so you can easily use the condition that d phi by dr at R equal to R naught is equal to 0. This is the condition for equilibrium. Utilizing this condition, we will be able to find the value of sigma over R. So you can see it here. In equilibrium, we can write d phi by dr at R equal to R naught is equal to 0. Okay? And now sigma is, phi is defined in equation 13. You have only to differentiate it with respect to R and then substitute R equal to R naught and try to find sigma over R or sigma over R naught. We will find it. So let us see, after differentiation, what will be our result? In first term, there is 1 by R to the power 12, which means R to the power minus 12, and its derivative will be minus 12 by R to the power 13. R to the power 13. So the first term becomes minus 12 into 12.131 sigma to the power 12 divided by R naught to the power 13. And in second term, there is 1 over R to the power 6, whose derivative will be what? That will be minus 6 by R7. That minus and the minus present already here, that will become plus. And so there will be plus 6 into 14.454 sigma 6 by R naught 6, and that is equal to 0. Okay. Now you can see when we will simplify it, actually this factor 2 n epsilon, and you can say sigma 2n epsilon sigma 6 R naught 7 into 6. This factor will be removed because in RHS there is 0 and we can take this as common factor. So what are the remaining terms? The remaining terms will be, here will be 2 times 12.131 sigma to the power 6 divided by R naught to the power 6. Okay, and plus here there will be minus sign, and plus 14.454 times 1, and that will be equal to 0. So from here you can easily say what will be the value of this sigma over R naught to the power 6. This will be actually equal to what? This is 14.454 divided by 2 into 12.131. Okay, and from here you can find the value of sigma by R naught, and then taking reciprocal you will get the value of R naught by sigma. So after making this calculation, it is found that R naught over sigma is equal to 1.09. 1.09. Okay. Now we will put the value of this R naught over sigma or sigma by R naught in this equation 13. Okay, in this equation 13, taking R equal to R naught, and then we will get the binding energy. So now binding energy is written by the symbol phi naught instead of phi, and after simplification you will get this is equal to minus 2.15 into 4n epsilon. Okay, this is actually the calculated value of the binding energy when the kinetic energy of atoms has been taken 0. You have seen in this case that we have never considered the kinetic energy of the atoms of the molecular crystal. We have only assumed the potential energy. Okay, so we have neglected the motion. So under this assumption, this is the binding energy of a molecular crystal. Okay, so in this way we have completed the calculation of binding energy of molecular crystal, and I hope you have definitely enjoyed this session, and if you have enjoyed, then you should write the comment, your comment in the comment box, and try to watch the complete video and the videos which will be actually come later on. Okay, thank you very much.